Okay, so I mentioned this application, so hopefully you've seen this website PHET before. But what I recommend doing is, again, this is lots of people have a really tough time grasping the difference between field, force, potential, and energy. So this application is very useful. So go to PHET, click on Simulations, Physics, and the one we're interested in is Charges and Fields. So I'm going to click on Charges and Fields, and I'm going to press play. So we get this. Let me just fit that in the window. So right here. So we get this app right here. So how this one works is we can place a charge. So for example, I'm going to place a charge right here, and we can see the electric field lines that result. So here's a positive charge. We already know that for an electric field that forms around a charge, it goes away from positive towards a negative. So if I actually get the center out, I can actually see the relative size. So notice how the electric field, when I get really close to the charge, it's really big. When I move that sensor further away, we can see the electric field gets smaller and smaller and smaller. You can also tell by the gradient of the intensity of light for the arrows. So notice the arrows are a lot lighter the further away it is. Notice as I move this charge, the electric field changes as well. If I put different combinations of charges, we can see what happens. So notice right now I have a positive and negative charge. We can see the electric field lines go from positive to negative. We can see different combinations. Like what happens if I have double the negative strength over here? Notice how when I add more negative charges here, you can see what happens to the electric field lines. Right? I can reset it. Again, it says play around. See if you can really understand what is happening with those electric field lines. The other cool thing that we can do with this application is look at voltage, electric potential. So I'm going to turn off electric field. And I just click on voltage. See that where it's brighter, it has a higher potential. But I'm going to use this instead, this thing. So notice how when I bring the sensor close to it, you see the equipotential, that's the voltage, is really big. So basically what it's doing right now is you can actually do grid lines and actually explicitly calculate the values. I can't remember exactly which one, but you can kind of reverse engineer it. But this is 1 nanocoulomb of charge, and when I'm this distance away, it's saying that the equipotential is 18.56 volts. So I can actually press this arrow button, and it's going to create a line. So basically what it's saying is, because energy is scalar, it doesn't actually matter which direction I go from. So it's actually creating a sphere around it, not just like a 2D circle, but this is a 2D representation. Everywhere along this line has the same potential. So I go further out, like out here for example, our equipotential, our voltage is 9.147. So our potential, the reason it's called equipotential because we're basically finding all the points of equal potential. So equal. So everywhere along this line has the same potential. So in itself, this value like out here, this is 5.982. In itself, this 5.92 does not interest us that much. What's interesting to us is that change. So if I have a charge out here, like for example, if I put like a negative charge here, it can just like a planet, if it's given the correct amount of velocity, it can just orbit around this positive charge forever. If I wanted to change its orbit, I'd either have to take away energy or add energy to either change its orbit to smaller or bigger. So the reason why gravitation was very easy because we have these concentric circles, these perfect circles of equipotential around it. But because we have point charges, it gets a little more complicated. So for example, if I now place 2 positive charges and I now take my sensor, we get values of different equipotential. So basically what it's saying is anywhere along this path has the same potential. So basically because these charges can be close together, we can end up having very interesting effects. So basically what happens with gravitation, the masses are so far away, you still only get these nice little circles. But because these charges are really close together, we can get these very different paths that could be followed. And the cool thing about energy, it is just a scalar value, so you don't have to do any vector addition. You literally just define the potential from one. Okay, so let me just turn the grid line so I can show you what I mean by that. So I see right here, if I look at this point right here, right now that has a voltage of 6.375. So remember that value. Remember that value. So make sure you write that down, 6.375. Okay. Now I'm going to move this charge right. Let's move right there, actually. Sorry, let me set that up again. So 6.375 was around there, right? 6.375. Now I'm going to put a charge right there. And right now the voltage is, that says 4.524 volts. So again, remember that number, write it down. Let's see what happens if I put a charge back to that original point. It's just going to be the addition of the two. 6.375 plus 4.524. That is equal to potential. Also, all we did was just add up the potentials of both of them. Our vectors, fields are a lot harder. So if I look at fields, if I take this one away, if I put a sensor there instead, you can see there's our field vector up and to the left. If I move this one there, my field vectors, sorry, or they're just straight up. I put here my field vectors up and to the right. If I now place a second one right here, you see the resultant is the combination of the two vectors. So field is a vector, potential is just energy. And we can do it with negative charges as well. So let's see what happens. If I put let's put my sensor right there. Right now it has 0 volts. If I put a negative charge right here, we have negative 9.080 volts. If I put a positive charge on the opposite side, guess what it's going to equal to? Oh, I hope you said 0. Again, it's not going to be perfect, but if I can get that perfectly equidistant, it would come out to be pretty close to 0. Right, so on its own, right, around 9 volts. 9 volts. I'm just going to add them together. So negative charges create negative potential, positive charges create positive potential. And if I put a charge, again, because it's scalar, it doesn't matter if it is the direction it is, as long as the distance is the same. So notice how there's my 0 volts, there's my 0 volts, right? 0 volts. Okay. Yeah, play around with it, see if you can make sense of this. And it's a very useful application that PHET has here.